Okay. Hi, everybody. I assume we need to speak in English here, okay? Who I am, my name is Andrea Gigli. I am a data geek. By day, I work on an investment bank and I manage a desk of trading. I also follow some projects in the data-driven fields, more generally. By night, I am a data scientist. I like to collaborate with research centers and universities. I also I'm a startup mentor and an event organizer. Probably some of you yesterday enjoyed Data Beers. It was an awesome night. My background is in statistics and machine learning. And today, I'm going to talk with you about recommendation system models. Before going on, keep in mind that all models are wrong, but some are useful. So why recommendation systems are useful for us? Because recommendation systems are an alternative, a very useful alternative to search engines. And if you think we are living in an era of information deluge and digital laziness, having a recommendation system is really helpful for us. Moreover, there are very successful stories around recommendation system. Think about Spotify, Pandora, or Netflix, Amazon. There are different types of recommendation system. How many of you have tried to implement a recommendation system? Please raise your hand. Okay, not so much, not so many. So I give you a quick introduction. There are three types of recommendation system. One type is called content-based filtering recommendation system. In this kind of recommendation system, we try to suggest something to someone on the basis of the features of the item set we want to suggest. In collaborative filtering methods, we don't care about the features of the items we want to suggest. What we care about is the relation, the similarity between customers or the similarity between items, where similarity are measured on the history on the observed history. We are going to see two applications of collaborative filtering methods. And as I told you, collaborative filtering methods don't require really an understanding of the features of the item set. We don't care if something is yellow, green, big or small. We don't care. It's an item. And they require a large amount of data in order to train properly the recommendation system. And we assume that people that who agreed in the past somehow will agree in the same way in the future. Why recommendation systems in banking? In particular, why recommendation system in portfolio selection? This is the application we are going to see. Because there are a lot of papers, tons of papers on portfolio selection models, quantitative portfolio selection models. All these papers, all these techniques are based on assuming that we know the features of the investments. We know the feature of the stocks. We know the feature of the securities we are going to invest in. They are very asset specific. Moreover, these models are built on economic theory, assuming that we know something like that all investors are risk adverse. But if you think about people which gamble in the exchange, buy and sell stocks, like flipping a coin, it's not really risk aversion. It's gambling. So models which are good only because there are beautiful formulas somehow are dangerous. We don't trust them. I prefer to trust in something different. I prefer to trust in something built on data. So in banking, in portfolio selection model, embracing this approach is like doing a paradigm shift. We are no more putting data and an economic model on the computer machine in order to get a solution. the number of assets to buy, but we are doing something different. We are doing to put data in our computer machine. We are putting some portfolios, observed portfolios, in our computer machine, and what we get is an algorithm to do recommendation on the basis of the history. So let's start with applications. The first application is based on graph theory. Graph theory is something applied, really, in the 18th century by Euler. Euler applied graph theory to solve the Königsberg problem. Königsberg is a city in the Middle Europe which has 7 bridges. And the Königsberg problem is it possible to find a walk through the 7 bridges without crossing a bridge twice? Euler showed that it's not possible using graph theory. What we do so? We now want to do asset recommendation, starting from information on customer portfolios. So we can split our information ideally in 2 components. A customer set and an asset set. We can try first to draw relations between customers and assets in this way. What I mean with these drawings. Customer 1 has bought asset 1 and asset 2. Customer 4 has bought asset 1, asset 4, asset 5. I built some relation between 2 disjoint sets, one of customers and one of assets. From this representation, I can build a graph of the relations among all the assets. Asset 1 and asset 2 have a link because someone has bought asset 1 and asset 2, customer 1, and so on. I build a graph from this observation. But just drawing lines between assets, it's not enough. I need to give a weight to these links. And I give a weight which measure the similarity between 2 different assets. And the measure I want to show in this simple toy application is just a similarity measure computed by the following ratio, where a numerator is represented by the number of counts of users which bought both asset A and asset J. The denominator is the sums of 2 counts, one given by the number of counts of users which bought asset A, and the other number of counts of users which bought asset J. The calculation is quite easy. For example, if I want to measure the similarity between asset 1 and asset 2, I just need to compute the number of users, customers, which bought both asset 1 and asset 2, which is 1. It's just customer 1. The number of users which bought asset I is 3. The number of users which bought asset 2 is 2. And the ratio, is 0.20. This is a measure of similarity between asset 1 and asset 2. So hands-on code now, let's try to implement this. We are going to build a similarity measure among the whole asset set and to build a recommendation system on the basis of these similarity measures. So first, the easy part. We just need to put somewhere in a data structure the assets count. So we simply build a dictionary. We assume that we have a file text, txt, a txt file, where we have recorded the number of counts for each asset. Very simple starting point. And we built a dictionary, asset counts, just by reading this file and putting the information on the dictionary. The keys of the dictionary are the asset labels. The values of the dictionary are the counts. Okay? So I'm building the denominator components, okay? The denominator ingredients. Now we have to count pairs. And our information is represented by portfolios, okay? I know that customer 1 has 4 assets in his portfolio. Customer 2 has only 2 assets, and so on. I know this information for all of my customers. So let's start from customer 1. I represent this information in this way, as a list, as a pile of couples. So I reported asset 1 and asset 2, asset 1 and asset 4, asset 1 and asset 6, then asset 2, asset 4, asset 2, asset 6, then asset 4, asset 6. This has been done for all the customers. I have a huge list here on a text file, which I call this time asset pairs. Okay? So now I simply need to count the pairs I have ordered in this way. So I build a new dictionary named dictpairCounts, which is simply built in this way. I read line by line the file. When I read the first line, I assign to a list the field, the second element of a list, the first asset and the second asset, and then I build a dictionary which count the pairs. Okay? And I do this process for all the rows of my file, obtaining a dictionary where the keys are the labels of the couples, of the pairs, and the values are the counts of the pairs. Okay? So I have both the ingredients for computing the numerator and the denominator. These ingredients are in my dictionaries. So let's compute similarities. Now it's very simple. I just have to iterate through the element of the dictionary and count the number of times each pair, and compute the ratio between the dictionary pair counts and the dictionary asset counts component. So what I need now I have a representation of my graph on the left in a dictionary, which has pairs as a key and values, and as a value, the similarities I have just computed. I want to obtain an ordered structure of data, because I want to have a system which is fast enough that if I input, for example, the name of an asset, asset 1, I get as a result an ordered list of similar assets, possibly ordered from the most similar to the least similar. So I'm going to build a dictionary of dictionary, where the key elements are the assets and the values are a dictionary of ordered asset, ordered account, ordered in function of the similarity. So this is the tricky part. What we do now? We have to build a dictionary of dictionary. We start by reading the elements in pair similarity dictionary, the dictionary of similarities. If the dictionary, I remember you, is composed of pairs labels and similarity measures. The pairs label is split in two components, asset I and asset J. And for asset I, if not present in the dictionary, I create a dictionary as a key element, as a value element, sorry. If asset I is already in the dictionary, in the dictionary of dictionary, we assign to the element asset J the similarity measure, and so on. And we repeat also for the second component of the pair. So at this point, we have built a dictionary of dictionaries where the keys are the assets and the values are a subdictionary. Is a subdictionary, where the subdictionary has as keys assets and values similarity with the key of the main dictionary. Now I have to order the dictionary of dictionary. What I do here is just for each pair in the dictionary, ordering the dictionary of dictionary accordingly, and saving the file in a txt. So in my txt now is something which can be queried very fast. Can be queried very fast and can return an ordered list of suggestions. So what I just need to do now is to read the txt I saved in my computer machine, and pass to the dictionary I have just uploaded the name of the asset for which we want to compute similar items or similar assets. And that's it. This is the first application. So we built a dictionary of dictionaries starting from information on the portfolio of customers. This is one application. The second one is inspired by a topic which I've seen very often reported in the program of this SPI conference. We say that markets are conversations. So maybe we can start treating markets element as words. How many of you know word embedding? Embedding? Okay. The idea here is, why not applying word embedding for building a recommendation system on investments? What word embedding does is mapping words in a vector of real numbers. In particular, word2vec is a particular technique to implement word embedding, taking inputs a large amount of text data and producing output a representation of the words of this corpus in a vector space. This representation is characterized by one important thing. Words which appear in the same context are close one to another. Context is relevant because context allows to give an interpretation of this vector representation. In particular, for example, the vector representation of Paris minus the vector representation of France plus the vector representation of Italy generate a vector real number, which is close to the vector representation of Rome. This is pretty amazing. And that's more, because you can also see that the vector representation of walking minus the vector representation of swimming plus the vector representation of swam is close to the vector representation of walked. It's fun. These British linguists say that you shall know a word by the company it keeps. But we can say you shall know an asset by the portfolios it belongs to. Okay. So we do asset embedding. From word embedding to asset embedding. So if word embedding can project words in a vector space, asset embedding can project assets in a vector space in such a way that the assets which are usually by together will be closer. And this is the kind of representation you get. According to the way you calibrate your model, you get somehow a representation on a space. This is a space in 2 dimensions, okay? Usually you have 100 dimension, 300 dimension. It depends on the number of assets you have and something you have to calibrate. You have to do hands-on calibration to understand which is the dimension of the vector space you want to work on. Let's try to see what can be done with this approach. We have our portfolios, as before. Now, we don't use a dictionary of dictionaries. We use something easier. We use lists. We use list of lists, actually. We can represent a portfolio as a list of elements, where each element is the asset in the portfolio. And we put this this list of portfolio together, list of assets together, and we get a list of lists, which is portfolios. Portfolios is a list composed of lists, and each element is a portfolio of a customer. There is a very beautiful library in Python, which is called gensim, which allows to implement word2vec. The code is very two-line codes, basically. You have to import the library and just run the function word2vec, giving input your list of lists, which in our case they are portfolios, and some information like the minimum number of assets you have to find in a portfolio to be considered relevant for the calculation, another feature which are model specific. I don't want to enter into detail of this. And you can get some information after training of the model, like the number of the list of assets in the portfolio of your clients and the vector representation of these assets. Now we have built a vector representation of the assets starting from the portfolios of my clients, of my customers. And I can measure similarity also using gensim library. Okay, now we have represented our assets in a vector space. Now we need to compute the similarities between these vectors. Similarities in a geometric space are distance. Closer vector means similar items. So I want to measure the distance between these items. I could use actually this function also, similarity function from the gensim model. I didn't talk about it. I use a cosine similarity from the SciPy spatial distance library. So I built, as before, a dictionary where for each pairs of asset, I have computed the similarity, and I saved the similarity in the dictionary. So as before, I can build a dictionary of dictionaries, order these dictionaries of dictionaries, saving the dictionary and querying it as before, like in the previous application. So we conclude. Okay. We conclude with a summary. We have implemented 2 toy models for recommendation system in financial services, one based on graph theory, the other on word embedding. Clearly, many more recommendation systems are possible, based on alternating least square, matrix factorization, and so on. But this, I think, is 2 very simple applications, right for a beginner's talk. Bear in mind that testing the goodness of a recommendation system is not an easy task, because usually in machine learning, statistical learning, if you have some data, you split the data in a training and a test set, train the model in the train set, and test in the test set. In this case, this kind of approach is biased, because if I have to pick up something on the basis of the information at my disposal, this doesn't mean that I could change my mind if someone say, hey, maybe you can be interested in this. If you think about this, when Cinderella's never asked for a prince. Cinderella just asked for a dress and a knight. Only after someone showed her the prince, she fell in love with him. A recommendation system are the same. To test them, you need to show to true customers. You need to do A/B testing and trying to improve continuously your recommendation system according to the feedback you receive on the A/B testing. It's very hard to test a recommendation system on paper. So this concludes my talk. Thank you very much.
Yes, we have time for some questions. Only 5 minutes because we start late. Did you test it on a real data set or
Sure.
a real environment? And
Sure.
in that case, what's the size of your data set? How many assets, for example? And do you have any idea of performance?
Okay, the number of asset was 1,300. And the dataset was a dataset, 1 year dataset on several hundred thousand customers. And the results were pretty promising. And we are trying now to enlarge the dataset, to do some data processing before giving data to the machine, to the computer machine. Because, for example, one feeling is that you cannot give to the machine, for example, the icing code, because you get too much granular data, and it's too much. You get too much sparsity, and you don't get very good results. But if you try to aggregate somehow to cluster at the beginning of the process the assets, then you get very good results.
Okay, thanks.
We don't ever tested with A/B testing the results yet.
Do you have an idea how to extend this model to also recommend new assets? I mean, if an asset
Something never seen, huh?
Yeah,
No,
exactly.
I have no idea. So far, I have no idea.
Thank you.
But actually, if you do aggregation properly, you don't need this. I mean, if, for example, if I train the system on a generic asset, an aggregate of assets, there is no problem of this kind. Yeah, contaminated, more or less. Yeah, you're right.
Hello, one question. Well, usually in recommendation systems, well, as you said, there is splitting between training set and testing set. Well, and have you tried to measure the minimum? Well, in this field, usually is used measure like average. Well,
Average under the curve.
no,
Rock curve.
squared average error.
Okay. We did
but
this.
have you tried in the test set and your trying set?
Okay, we tested actually something in this way, and we get good result. But
How much? How much?
75. Okay, we compared the recommendation made by saying I want to suggest to customers the most sold, the most bought item. Okay, and we get an improvement of 20% on this. But I think it's quite a random result. I'm not confident about this result because of the reason I told you, because it's really what I want to get when I build a recommendation system is something which gives new information to a customer, something different of the information set on which he chooses normally. So if the information set I want to test is not in the data, because it's missing in the data, how can I test something?
Those usually comes from scientific literature,
Yeah.
and they try to invent a measure to how to compare models. But it's different from business. I can understand that. So thanks.
But how do you say the name of the measure you mentioned? Maybe
Average square error.
Okay.
Okay. Yeah.
I think in this case it's more appropriate using something which try to compare the number of the growth of the true positive against the growth of the false positive over the true negative against the true positive. And maybe
threshold.
Yeah, but I mean it's too good. I don't.
Scientific. I'm business.
Because
Definitely.
if you think about if I go to my manager and say I built a recommendation system. Okay, let me see what I've bought the customer and what you've recommended. It's a disaster because you have to pick up something in 1,200 items, and it's very easy to be wrong. It's very easy. So odds are against you, absolutely.
Thanks for the talk, very interesting. And I think that the idea of using embeddings for the recommendation is very interesting also. And you are using similarity between the vectors to find the most similar ones. But do you think that maybe recommending the most similar is not something like recommending almost exactly the same thing, and which other types of similarities you can use to do this?
Results say it's not true. And I was impressed because you can see, okay, I have a data set which is a bit biased because there are a lot of people buying bonds. Okay, so I have a lot of bond buyer, many stock buyer and ETF buyer, some funds. But what you see is that if someone has bought a bond and you insert the bond, you see that in the second or third position you also get stocks. Maybe it's a chance. No. The data set I think is too small to draw conclusions. And the intent of this talk is also to receive feedbacks, because for me it's very important to have some guidelines, some idea, something new to try. But it seems they are suggesting also something different. If I suggest bonds with a very good rating, I also suggest bonds with middle rating. So there is differentiation. So it could be, I think it's promising.
So actually there is no time for no more questions. I mean, if it is something very, very fast, it's okay.
As you like. Not yet. Not yet. I agree with you. It's the next step. Okay. To build somehow to train on a weighted set and not on an equal weighted set.
Okay, thanks everybody. Thanks Andrea Gigli.
Thank you.